Hello, and I would like to perform some intuition about magnets. That is, the observations we make about magnets themselves. Okay? So we will be observing here in this video magnets, magnetic fields, the effects that magnets have on charges, and things related to that, like magnetic domains and so on. So let's go ahead and see what typical observations of magnets are going to be. What I have here is a typical bar magnet. Many magnets have the geometry of bar magnets. That is to say, they have a north pole and a south pole, and the entire bar is a magnet. We sometimes call these permanent magnets. Now, even though we sometimes call it a permanent magnet, it can be unmagnetized, but it's very hard to do. It's made sort of in a laboratory or machined that way. And we assume this magnetic field is very strong and it's nearly permanent, almost permanent. So let's go ahead and see what the effects are of putting a compass nearby. Now, a compass, by the way, was first looked at by the Chinese. It turns out that magnets are named after a region of Greece called Magnesia. And they noticed that certain rocks would attract one another in the region of Magnesia, and they weren't really sure what was going on. The Chinese were the first to use compasses and compass needles, and so we know a compass needle reacts to magnetism. So notice when we bring this compass needle nearby this magnet, notice that the compass needle changes its direction. And it seems that there is a magnetic field nearby the bar magnet. So let's go ahead and actually show what that field is. Notice that if we have many sort of imaginary little compasses, you'll see that the compass lines are affected by the space around the magnet. That is, the space around the magnet is indeed a magnetic field. Notice as I move this compass around, it aligns to the local magnetic field, which is in that region. Also note that if I move the compass quickly, it takes a while for the compass needle to reorient the local magnetic field, and there's a torque on that compass. Not a force, but a torque, because it's a rotational force. Notice this looks somewhat different than an electric field, but there's definitely also some similarities. Do you also notice that these magnetic field lines, let's see if I can trace sort of a magnetic field line here. Okay? So I'll try to trace this magnetic field line here. Notice that it seems to go out of the magnet, out of south, into north, and if we actually show inside the magnet, it continues through the magnet such that it seems to have sort of a closed loop. And what I mean by a closed loop is that there's no beginning and no end to the magnetic field. That is to say, these magnetic field lines don't start and end somewhere like they do with positive and negative charges in an electric field. They don't have a genesis and terminus point. These magnetic field lines actually form closed loops. Now, I don't necessarily mean closed circles, but closed curves, closed field lines. Okay? So that's a very special property of magnetic fields. Okay? That in some sense, magnetic fields exist within permanent magnets. Now, by the way, if you look at the coloration, the magnetic field is strongest near the ends of the bar magnets, and it's weaker as you go outward. That's meant to be shown by the brightness of the coloration of these little imaginary compasses nearby. Also note, if I increase the magnetic field strength by increasing the strength of the bar magnet, you will see that this is even more pronounced. So you have even stronger magnetic field here and here, and the magnetic field is still weak, pretty far away from the magnet. It turns out magnetic fields will also still follow the inverse square law in terms of their intensity. Now, by the way, the inverse square law equation for magnetic field is actually a lot more complicated than Coulomb's law is for electric fields, but we'll get to that. Let's see. Also, important to note is that if we show a field meter, now magnetic fields don't have these units here, at least in terms of SI units. The SI unit of magnetic field is going to be the Tesla, okay? It's going to be capital T. But it turns out 1 Tesla is a very, very large magnetic field strength. By the way, a Tesla is named after the Serbian physicist Nikola Tesla, who was working on electric motors in the late 1800s. Okay, kind of the closest thing we ever really had to a true mad scientist. Okay, so since 1 Tesla is a huge magnetic field, instead we usually measure things in this unit. So capital G is what we call Gauss. Notice that very close to the south pole of this magnet, or very close to the north pole of this magnet, we have a strong magnetic field. And 1 Gauss is 10 to the minus 4 Teslas. By the way, notice that you can see the direction of the magnetic field from both the compass and the meter here. So let me move the compass back over. Notice the X component is shown to be positive here, and the Y component is shown to be slightly negative. Okay? So that's because by convention, we assume magnetic field lines come out of the north end of a magnet into the south end of a magnet. That's the convention we use. Just like that charges, positive and negative charges, had positive to negative was the direction of the electric field. Notice this little compass needle right here, so very similar to this one, points down and to the right in terms of the red. The red being the north end of the magnet, the white being the south end of the magnet. And notice that, again, that means the X component will be positive, but the Y component will be negative. So if to the right and down is positive X and negative Y, then that's what we would have. But over here, even though we have similar magnetic field strengths in terms of their magnitudes, the X component is positive and the Y component is also positive, because these little compass needles over here are moving up and to the right in terms of their magnetic field direction. Okay, so let me in fact show what planet Earth looks like. Now here's planet Earth. Planet Earth is what we often call a magnetic dynamo. Now, for reasons I have not explained yet, in order to have magnetism, we must have moving charges. No moving charges, no magnetic field. Now, you may say, wait a minute, what about the bar magnet? I don't see any charges moving there. Well, it turns out they're moving on the subatomic level. They're either spinning in sort of a charge way, and it's sort of subatomic, and it's sort of a quantum physics way. Some of that's really beyond the scope of this video. Or they're all sort of rotating together. That's why many metals do not exhibit naturally occurring magnetism. Naturally occurring magnetism is very uncommon for a metal. So only a few metals are sort of naturally occurring magnets. Okay? So if we show planet Earth, it turns out, where are the moving charges? Well, even though we've never burrowed into the Earth more than 18 miles or so, or 30 kilometers, I don't remember the exact number, it's something on that range, and the temperature is really high, even though holes have been dug that deep, we hypothesize that the interior of the Earth is molten rock. And because it is molten rock, there are convection currents. Now, if you know anything about thermodynamics, you know that warm fluid tends to rise and cool fluid tends to take its place, sort of sinking on the edges. And these convection currents seem to be reflective of spreading of geologic plates and so on and so forth. But anyway, what we're trying to say is that we also assume that there are some magnetic metals in the interior of the Earth, and the moving charges in these convection currents create Earth to be a magnetic dynamo. That is, the Earth has a naturally occurring magnetic field. This naturally occurring magnetic field produces a field that surrounds the Earth. Now, by the way, this is actually very important because charged particles tend to get deflected or absorbed, for that matter, by Earth's magnetic field and bombard the upper regions of the atmosphere, especially in the polar regions. So because of this magnetic field, we are saved from those charged particles that come from the sun. That we call the solar wind, coming from the sun. Also note, interestingly enough, the north end of the bar magnet that you can imagine is related to the Earth, and the south end of the bar magnet are not at the geographic north and south pole. Geographic north pole tends to be up near here, but notice that the magnetic south pole tends to be roughly in the Hudson Bay area of Canada in the northern hemisphere. Whereas the magnetic north pole is definitely in the southern hemisphere, but not at the geographic south pole. Okay? So interestingly enough, Earth's magnetic field lines come out of north into south, but what that means is a compass needle, which has that red line, should point towards geographic north, but geographic north is actually magnetic south. So what that means is if you have two magnets, and one of which is a north pole, that's this red, and the other side of the other magnet is south pole, north will attract south. So when you move the compass needle down here, south will be attracted to north, but north is repelled by north. So like poles repel, and unlike poles of magnets attract. Now, again, by the way, even Earth has a non-uniform magnetic field. It's not a nice, beautiful, straight geometry. The magnetic field is quite a bit stronger near the geographic poles than it is out here on the edges. Okay? Closer to the equator and so on. Okay. So if we show Earth's magnetic field, so we can look at the strength of Earth's magnetic field at various places, but one thing we note is that Earth's magnetic field has various values, but we usually say Earth's magnetic field at any given place on Earth is approximately about 1/2 of a Gauss. So about 0.5 Gauss, which would be about 5 times 10 to the minus 5 Teslas. So again, magnetic fields are often measured in Gauss, even though the SI unit is Teslas. Okay, let us take a look then at another example where we actually plot some magnetic field lines by hand. So what I have here is a Professor Walter Fenn simulation of the magnetic field of a bar magnet. The only difference in Professor Walter Fenn's scheme is that he uses red for the north end of the magnet and green for the south end of the magnet, as opposed to red and white. Okay, so we see that convention up here. Notice as we move this compass needle around, we see what these magnetic field lines look like. Notice that indeed they are closed loops. They go out of north, if you look at the arrow convention, and they go into the south. Notice I can also move the needle around in terms of kind of the strength. So what I'd like to do is I'd like to plot a few magnetic field lines. So let's plot this one. Let's plot a roughly symmetric one over here. Let's plot one that goes straight through the center. Let's plot one on this side. Let's plot another one that's roughly the same size on this side. Let's plot a few that are close by, and hopefully you're kind of getting the idea of what magnetic fields look like. Okay? So, notice that there definitely is some symmetry to these magnetic field lines. In fact, there's symmetry down from north to south, but there's also symmetry this direction. So, at least for a bar magnet, there's two symmetries, here and here. Notice, again, magnetic field lines come out of north into south, go through the magnet itself, and again, they have no beginning and no end. So these closed loops, this is very different than electric fields, or electrostatic fields, or charge particles. Remember, magnetic fields are generated by moving charges. Okay? If I clear the field lines, and if I turn the magnet around, hopefully we should see the magnetic field lines going in exactly the opposite direction. So hopefully I can just prove that to you here. I'll just show a few magnetic field lines. Okay? And hopefully you get that the convention is, again, out of north into south on these closed loops. Okay? Let's have a look at another example where we are able to look at magnetic domains. Now let us examine magnetic domains. So what I have here is I have a regular bar magnet and I have a paper clip. This is supposed to be a very zoomed version of pieces of iron or pieces of material that are part of the paper clip that have the possibility of a magnetic domain being reoriented. Notice a paper clip will contain usually a little bit of iron. Now there are many magnetic metals out there, but by far the most commonly occurring magnetic metal in Earth's crust is iron. Now I believe Fe is the symbol on the periodic table for iron, and that symbol is related to the Latin word, I believe, ferric. Okay? So we often say if a material is ferromagnetic, in other words, it can be magnetized or it can exhibit magnetic properties. So what that means is we should be able to magnetize it, or at least like temporarily create a magnetic field inside the object. So in fact, that's what we're going to do. We are going to reorient some of the randomly oriented magnetic domains of this paperclip. So think of these arrow directions as the pointing directions of little bar magnets. And that little arrow is the direction that's pointing from the south end to the north end of a little bar magnet. Notice when we bring the north end of this bar magnet nearby, we're going to do this slowly, and you'll start to see the magnetic domains will start to align. And in fact, look at that. The magnetic domains are now aligning. They're roughly starting to point more so downward. Downward because the strong external magnetic field of the bar magnet is influencing the magnetic field of this paperclip. If I bring them closer and closer, there's greater alignment. And if there's enough alignment, we create a strong magnetic field in the paperclip, and we can actually pick up the paperclip. So many of you know this, that certain things can be picked up by strong magnets if we reorient the magnetic field, that is the magnetic domain. If I reset and I instead have the north end of the magnet pointing upward and the south end of the magnet pointing downward, notice we'll bring the bar magnet down. Notice we're going to again reorient the magnetic domains, but this time the magnetic domain should point upward from south towards north, and again we'll still pick up this paperclip because we've strongly reoriented the magnetic domains. But notice something. The magnetic domains are now upward. do you see that we attract the paperclip whether we have the north end or the south end of the magnet pointing? That's very similar to polarization with charges. Remember, with polarization, you're going to get attraction either way. As long as a material can be polarized, whether it's a negatively charged rod or a positively charged rod, either way, if that material can be polarized, you still get attraction. So in some sense, attraction is more common than repulsion. If we're going to repel from a magnet, we know we have to have another magnet nearby. And in fact, we have to have the same pole, north repels north, of another magnet nearby. Let's have a look at another example, but this time with a moving charge through a magnetic field. So what I have here is I have a charged particle in motion in a magnetic field. And in particular, let's let the red vector be the vector velocity of this positively charged particle. Let's let this gray vector here be the magnetic force. So we haven't talked about magnetic force yet, but we will. Let's let this little dot here be the center of the circle that it's rotating around. And let's also let this particle be in a uniform magnetic field. That is, the magnetic field is roughly straight and equal magnitude everywhere in this plane. Now, by the way, you may ask, what direction is it? Well, do you see those little blue X's everywhere? Those little blue X's, like this, indicate that the magnetic field is into the page. So into the page is perpendicular to the plane of the screen of this video. So sort of going straight into your television or your phone or your laptop, whatever. Now, also, we could change the magnetic field that it could be out of the page. But if the magnetic field was out of the page, it would be dots, not X's. The convention for that actually comes from X's, come from if you fire an arrow, you see the back of the arrow, the feathers, that looks like an X. But if an arrow is coming towards you, you see the tip, that looks like a dot. So that's where the convention comes from. Okay, so a charged particle moving in a uniform magnetic field should actually move in a circle. And the reason for that is because magnetic forces are actually perpendicular to the charged particle motion. Okay? And the reason for that is because we were saying before, magnetic field lines have no beginning and no end. So because of that, they don't accelerate charges, they actually deflect charges. That's different than electric fields. Furthermore, magnetic fields tend to do no work on charges. They only cause charges to have centripetal forces, that is, directional forces. Okay? Keep in mind, right, this is kind of what we saw with the compass needle. When you moved the compass needle around, you had a torque, which was a rotation, not a net force. Okay, but anyway, let's have a look at this charged particle. So let's think about how we can change the size, or the direction for that matter, of this charged particle. Let's think about what happens if we increase the strength of the magnetic field. So I think there should be a greater magnetic force. So if there's a greater magnetic force, there should be a greater centripetal force. And I think we should also have a smaller radius of the circle. Hopefully you see that. Notice these X's got greater. That's because the magnetic field strength is greater. But if you have a stronger magnetic field, you have a stronger magnetic force, and the centripetal force here is greater. So the radius is smaller, and I think the time to make one rotation is less. Okay, so there we go. Let's try another situation. Let's see what happens if we make the charge twice as much. Now think about this. If you have, let's say, twice as much charge, that charged particle also experiences a larger magnetic force. Why? Because if you have a greater charge, it has more, well, charge that gets deflected. So indeed, we see the same effect that we had before, but not because of magnetic field, but because of charge. So if we have 2 times the charge of a proton, because it's positive, as opposed to 1 times the charge, it should have half the radius. And the period should be also less of the rotation. Okay. Now let's see if we change 1 or 2 more things. What if we double the mass? Well, if we double the mass, I think we have more momentum for the charge. So if we have more momentum for the charge, I think the radius of the circle is going to be greater, and the time period should be larger. And that's exactly what we see. If we have a more massive particle, so if this thing is 4 times the mass of an electron as opposed to 2, we should have twice as large a radius of the charge. Okay, let's go back to our basis here. This is our basis experiment. And what about the speed? Well, the speed, we can make the same argument as mass. If we have twice the speed, instead of 2 times 10 to the 6th meters per second, if we have 4 times 10 to the 6th, we should have twice the momentum, and we should have twice the size of radius. And that is what we see. So notice that we have twice the radius, okay? And we'll have to think about the period here, because we definitely are moving faster in terms of a tangential velocity. Now you may ask, how can you have this particle go around instead of counterclockwise? How can you have it go around clockwise? Well, first things first, by the way, let me mention why it is counterclockwise. It's because of a cross product. It's because of what we call the right-hand rule. It turns out that if the charged particle is, let's say, at right there, moving northward, and its velocity is up, we perform the right-hand rule in such a way. We perform QV cross B equals F sub B in terms of the direction. That is, the velocity of a positively charged particle cross product with magnetic field, the thumb should point in the direction of the magnetic force. So right there, QV cross product into the page with B, which is the magnetic field. The thumb should point in the direction of the magnetic force, which when the charged particle is right there on the right-hand side of the circle is centripetal to the left in the diagram. Now, even as the charged particle goes around, anywhere you perform that velocity cross the B, the thumb should always point towards the center of that circle. So hence why we have uniform circular motion. Circular motion at a constant speed. Remember that from Physics 1 class. Now, how can we change the direction of the the direction of the circle? Well, if we change the charge from positive to a negative, I think it should go the other way. Now, if it goes 0 charge, it shouldn't be in a circle at all. But if it's a negative charge, I think it should go clockwise as opposed to counterclockwise. So hopefully you can see that. Let's go back to positive for counterclockwise. Now, even though I can't change it on here, if I did change the magnetic field, instead of being into the page, if I could change it to being out of the page, the charged particle would also go clockwise. If I change the magnetic field to 0, notice that the charged particle should just follow Newton's first law and inertia. Okay? So in fact, it's off the screen. Okay? So, hopefully this makes sense in terms of how charges are going to be in uniform circular motion in a uniform magnetic field. Let's take a look at an example where a charge is moving in that circular path in a plane, but it also has a velocity, that is a constant velocity, perpendicular to the page. Now what I have here is I have a charged particle which is still in uniform circular motion, but what you see is that that's only in the YZ plane. In another plane, namely the XY plane, the object is moving, but it's also moving in the xz plane. That's because it has an x velocity. It has a constant velocity that's parallel to the x-axis. So we have to think about this three-dimensionally. Notice that the particle in the xy plane seems to go sort of up and down like a wave, similar in the xz plane. But if you view it three-dimensionally, the constant velocity in the x direction combined with uniform circular motion in the yz plane creates a helix path. Sometimes we call this helical motion. In fact, if you increase the x velocity, you'll see that we just stretch the helix out, that it covers a greater distance in the same time in this helical path. Notice, though, we haven't changed its motion in the yz plane. It's still moving in uniform circular motion. Now, you may ask, why is this important? Remember, earlier in the video, I mentioned that charged particles bombard the top of Earth's atmosphere. Well, those charged particles tend to rotate around magnetic field lines in a helical path, and they tend to collide with molecules in Earth's upper atmosphere, and they tend to ionize them. And when they ionize them, the energy is released. After the energy is absorbed, the electron gets boosted up to a higher level, then comes back down to a lower level to its ground state, but then it releases a light photon, that is an electromagnetic wave that's visible that our eyes can see. And hence we have the aurora borealis, or the aurora australialis if we're in the southern hemisphere, but the aurora borealis being the northern lights in the northern hemisphere, whereas the other one is the southern hemisphere. Charged particles that move in helical paths, sort of rotating around these magnetic field lines in Earth's upper atmosphere, those charged particles are the ones that tend to produce the aurora. And sometimes with the aurora, you'll see these really interesting looking sheets, kind of these large looking, sheets of charge where the charges have ionized particles in the upper atmosphere. Those sometimes tend to follow upper level winds and things like that, but anyway, it's pretty interesting. Now let's look at an example of what we might call a velocity selector. And a velocity selector is often how displays work in certain CRT machines, that is cathode ray tubes. This is especially used often in radar. It was especially often used in older television screens or older computer monitor displays and so on. Some of the technology in modern times is a little more advanced than this, but the principles are still there. So imagine that there's a very hot filament over here such that we can have charges come off of that filament with a certain velocity. Notice we can set the magnetic field magnitude and the electric field magnitude here. Now the electric field magnitude, we should know from earlier in the class what happens with that. A positive charge should move toward the negative plate here by electrostatic repulsion from the positive and electrostatic attraction towards the negative. That's a manifestation of Coulomb's law and electric fields. Fine. But with magnetic fields, we should also have a magnetic force. So we should do V cross B, and V cross B is going to be the direction of the magnetic force. So if V is to the right and magnetic force is into the page, that is the X's, then the force should be upward. Now I think in this particular case, both forces should be upward. So after we launch this particle, the red arrow being the velocity vector, its path should curve upward. Now by the way, depending upon strength of electric fields and magnetic fields, we can direct charged particles to hit this plate wherever we would like. Okay? So the particles moved out of the field of view. Let's go ahead and reset. Okay? And now, let's suppose we want to try to get it through this opening. So maybe let's make the electric field go the opposite direction. Okay? So if we launch again with the same velocity, the magnetic force is upward because that's QV cross B is upward by the cross product. But the electric field is downward, so the Coulomb force is downward. But notice now we're actually going to strike one of these gray plates. Okay? So it turns out that depending upon where you want the object to go, in other words, you want to select a certain velocity that hits at a certain place here or goes through this hole, you can actually calculate what the magnetic field is that you need it to be and the electric field of what you need it to be for it to go anywhere of interest. Now, let me go ahead and show you what a magnetic field in the opposite direction looks like. So I mentioned this earlier in the video, but those dots mean the magnetic field is coming out of the page toward you, as opposed to the X's, which is into the page. Now, if that's the case, the magnetic field is out of the page, then we got to do Q cross B, QV cross B, and then the magnetic force should be down, even though the electric force is upward. Now let's make our electric force kind of weak. So let's see if we can kind of launch this through this opening. Okay, looks like the magnetic force is a little bit larger than the electric force in this case, and it looks like we might even crash into the bottom plate. Okay, so that's what's going to happen. So green here being the trajectory of the particle. Okay, now by the way, again, I'm just kind of somewhat randomly choosing these numbers, whereas you can choose different horizontal velocities here, but you could calculate what the total force is by Newton's second law, and you can use constant acceleration to calculate, using kinematics, what the trajectory of this particle should be. Finally, for this video about magnetism and charges, we have what we call a mass spectrometer. Notice a mass spectrometer is very similar to the velocity selector, except that when the object is fired through these plates, we want it to go through this opening, and then what we want it to do is we want it to enter only a magnetic field. And when it enters only a magnetic field, it's going to follow that circular path and it's going to land at a certain location. Now we know that if we have greater mass, we should have greater momentum and then land at a larger radius. So what this means is that we can fire a certain amount of mass and get objects to land at different radii. So notice this charged particle is moving through the velocity selection place. It enters the magnetic field, and then it has a certain radius. Okay? So let's go ahead and see what happens when we have, let's say, a larger radius. So let me see if I can wait for a larger larger mass here, okay, and certainly a larger velocity. So let me launch, and notice that it should land at a different location. Okay, so indeed it will land at a much different radius. Okay, in fact, this radius is going to be quite large. In fact, we would have to make this magnetic field even larger. It would eventually land somewhere way up there. Now you may ask, what are mass spectrometers useful for? Let me reset and show you a different one while I talk here for a second. Okay? Mass spectrometers have been used to separate out isotopes of elements. Now you may say, separating out an isotope of an element, who cares? Actually, that's very important. Hopefully many of you watching this video have heard of the so-called Manhattan Project, the secret United States government project between 1941 and 1945 in which they built a few atomic bombs. They used things like mass spectrometers and even gas chambers to separate out uranium-235 and 238, the latter being the radioactive one. Uranium is a radioactive element, but only in its 238 form. Originally, they were only able to get about 1 microgram per day, but then eventually they started to get greater and greater quantities by improving their methods. So, this actually has very important historical significance. One more thing I'll say is that modern mass spectrometers are used for medical applications, so much more healing as opposed to destroying. So thank you very much for watching this video. Please go ahead and hit that like button if you like the content of this video and this channel. Please go ahead and also subscribe to the channel to grow the channel. Please share this amongst your social network. Thank you for watching High Peak Education, and I will see you in the next video.